And Shane, let's turn it over to the next item with an update on the computer-based train control.
Yeah, thank you, Chair Foley, Directors, Shane Edwards, AGM of Operations. The next item is for information on the CBTC update, and presenting today will be Lynn Williams.
Good morning. Can we bring up the slide? Thank you. Good morning, President Lee and board members. I'm Lynn Williams. I'm the Assistant Chief of Core Capacity, and it's exciting to bring you this update on communication-based train control. This is the modernization project that increases the frequency of trains and improves the reliability of the system. So it replaces and modernizes our 50-year-old train control signaling system. I'll keep it easy to understand so you can take away the basics of communication-based train control, which we'll refer to as CBTC. You'll see how the current system runs with what are track circuits that used fixed blocks and how it will run more effectively with moving blocks. You'll get updates on the significant level of effort and progress that has been made on the design, including starting construction and the manufacturing of components for the Hayward test track. You'll gain insight into how CBTC will roll out across the system and a look ahead for the project. Okay, to understand the future CBTC system and its benefits, let's walk through how the current train control system works. It's made up of a series of blocks along the trackway. This is showing a train moving across the track. The track circuits are organized into fixed blocks, and they're adhered to the track. They're anywhere between 50 and 1,200 feet long, and typically a 10-car train covers approximately 2 blocks as shown in this animation. Okay, the trains must have 2 track circuits between them at all times. That's where you see on the screen where it says buffer. A train cannot advance until the train in front moves further, putting greater than 2 blocks between the 2 trains. This is how a fixed block system limits the quantity of trains in the system. The speed is also fixed within a block. So, as you saw in the animation, throughput is limited with the current fixed block system. There are additional limitations to understand with this system. There is no flexibility to change speed codes within the block. The speed codes are also limited to specific speeds, such as 27 miles per hour, 50 miles per hour. These are the only speeds that the trains can go. Another limitation, the headway or distance, I mentioned it before, is limited to 2 track circuits, which on average is around 1,500 feet. Now, due to these constraints that speed and frequency cannot be changed, it is very difficult to recover from delays. On the physical side, the physical limitations, the 50-year-old track circuits reside in and beside the trackway. These are impacted by weather. Significant heat and cold result in faults, causing disruptions to service. The current equipment is located within the wayside, so in the event of an equipment failure, it requires blanket work or single tracking around the track in order to service it. In addition, cabling and fibers are impacted by rodents, chewing on them, due to the access points that have opened up over the many years, resulting in damage to this equipment. So now you understand the limitations of the 50-year-old equipment of this signaling system. There is also a significant operational limitation to understand. The Y. We mentioned it earlier. Here you are looking at the Y. Did you know it's spelled W-Y-E? And it is a triangle of railroad tracks used for turning trains. There's actually a technical definition for that. There is a series of tracks in the center of Oakland, and we know where it is. It's between 12th Street, Lake Merritt, and West Oakland. It is the heart of BART that pumps trains through the system. The Oakland Y is the geographic center of the BART system, and it is the bottleneck for the whole system because every regularly scheduled BART train, except for the Oakland Airport Connector and eBART, passes through it. So before we discuss the milestone of getting 30 trains through the Transbay Tube, they have to get through that Y. So let's look at the system map and see how the trains line up to get through the Y. Now, here's the big picture. How and where the trains are going to line up through the Y to get 30 trains within an hour to the Transbay Tube. We take a look at Richmond at the top of the screen. It takes about 25 minutes to get to West Oakland. So there would be about 4 trains between the end of the line and the start of the TBT, and this line will continue to feed trains into the Y during that hour. Okay? For Antioch, it takes about 45 minutes to get to West Oakland from the transfer platform. So there are about 7 trains between the end of the line and the start of the TBT. And down at Berryessa, it takes roughly 55 minutes to get to West Oakland. So the trains you see on the map would already be in the system when that hour starts. And additional trains will come from Dublin and Pleasanton. But you can see from this graphic that there has to be trains filling the system as close together as possible to get the 30 trains through the Y, which is the final milestone for the contract. Let's look at some animation up close of how the CBTC train control system works and how it brings the trains closer together. All right, this is a whole different concept. Here there are no fixed blocks or speed codes. The only limitation between trains is a safety distance. The trains communicate through radio signals between the train and the OCC and back to the train. The trains can accelerate or decelerate depending on the location of the train in front of it and the design of the track. We can go to a 2-minute headway, recover more quickly from delays, and not have the types of delays from an old 50-year-old signaling system with this new state-of-the-art moving block system. There are more benefits to this system as well. You know, throughout our day, from searching online to mapping directions, technology tells us exactly where we are at any time and has revolutionized our lives. CBTC does that for rail transit. The evolution of the technology and the experience gained in operation over the last 30 years means that modern CBTC systems are more reliable and less prone to failure than older train control systems. CBTC offers a smoother ride since there's no longer a transition of traveling from one block to the next where the 2 blocks may be at a different speed. We've talked about the frequency. You now understand how we can increase the frequency of trains. Trains can be more in the system at one time. New technology. Rebuilding the BART system for today and the future requires the need for new technology, and CBTC, it's a more sustainable system. We are able to increase service without increasing actual tracks, and it's more maintainable. It's able to be upgraded and keep up with technology and innovations through software. With all of these benefits, let's look at how we transform the system into CBTC. Let's start with the basics. Okay, there's 3 areas and equipment identified here on the screen. There's vehicles, software, hardware, and wayside. The colors on the screen correspond to these equipment types and general locations. So looking at the image on the screen, starting with the rail car in the center, it has a computer on board the train. That's called a car-borne controller. This connects all the functions of the vehicle to one computer. There's also an antenna on the roof and a speed sensor on the axles or near the wheels. The equipment that is along the trackway, it's called a transponder, and it goes between the tracks. This acts kind of like the fast track pass. You know, so when a train travels over the transponder, the signal from the transponder sends a message over. There's a blue box that says transponder interrogator antenna. Those 2 talk to each other, and then it sends the signal that tells the antenna. The message is, it gives the direction, the speed, and the location. This information is then shared there's a rooftop antenna. And then over here on the wayside in the train control room, there's a series of software and hardware that is installed, and each performs a unique function. We have this local ATS, front AM, but basically each one of those manages vehicle data, or operations of the interlock. And then there's additional equipment installed wayside. There's a box there called a zone controller and a wayside wireless antenna. The whole system is tied together with the computer and software at the operations control center. The antennas use radio communications that enables trains to detect their position from each other and from locations along the trackway. So how will this be implemented at BART? We issued a notice to proceed to Hitachi STS as the contractor to execute this design-build contract. What is in the scope of this project and contract? I'll just highlight a few that are on the screen here. I want to bring your attention to the top. The first is testing concepts and installing CBTC equipment at the test tracks at the Hayward test track. This work has already started with duct banks and cables being installed. The scope covers implementing a new automatic train supervision system. This is the software technology produced and designed by Hitachi. This is one of their core products. It overlays into the existing software at the OCC, and it will enable us to run the system with CBTC in one area and traditional track circuits in the other as we migrate through the system. This isn't a big bang approach. Everything is phased. So we have to figure out how do we run it in a phased approach. There are 2 milestones in the contract. The first is it will enable us to meet the capacity of 28 trains per hour through the Transbay tube with the phase 4 implementation. And you'll see at the end where the phase 4 is. The second milestone is the final capacity of 30 trains per hour through the Transbay tube occurs after implementation through phase 8. This is across the entire system. I have a slide coming up that will show you the various phases, so we will get to see that. But let's delve into the specific scope of work for the 3 areas and equipment that has been identified. Are you with me? Yes. Okay. I know, it's long, but this is fascinating. So we've got wayside, software, hardware, and vehicles. This highlights these 3 concurrent areas of the project happening at the same time. And up at what you see on the screen is just a glimpse in the types of equipment that will be installed on this project. On the wayside, it is an incredible amount of equipment. We've got 4,500 transponders between the trackway, 1,100 radio antennas, miles and miles and miles of cable and fiber. If we talk about the software, I mentioned it's not one type of software. It's software at the OCC, software in the computer wayside, and software on the vehicles. On the vehicle side, it's multiple types of equipment that BART forces will be installing. I've got more information to show you on what it will take to transform a train into a CBTC equipped train. And I'm excited to share with you the progress that we've made thus far. On the wayside, performed by the contractor at the Hayward test track, under the ground you'll find 320 feet of buried duct bank and 90 feet of armor cast cable. Surveys and assessments are ongoing at the W line and the M line. Wayside progress includes the enabling work. Thank you for approving the latest construction contract to improve the infrastructure at the K line. This is critical to our project. BART forces have been performing enabling work and will continue to during the process of rebuilding interlocks. For instance, when an interlock is replaced, we install a duct bank underneath the new trackway to carry future CBTC cables and fiber. Train control rooms have had asbestos assessments and abatements performed already, as well as work in the train control room throughout various lines. Okay, moving on to the software hardware progress. This is by far my favorite. So this CBTC project, it's difficult to physically see the results Until now, that perception has vanished. A few weeks ago, myself and a small team, we took a trip to the Hitachi Center of Excellence in Pittsburgh, Pennsylvania. This photo captures the work that is being completed at their manufacturing facility in Batesburg, South Carolina. What you are looking at is BART equipment under construction, under manufacturing. It shows the cables and racks and servers that will be installed, tested, and sometimes destructively tested, and then to ensure that it can withstand our elements like fog and sun, and then rebuilt again. These racks and servers will be loaded into a train control room in South Carolina and then unplugged, and the whole train control room, then filled with all this equipment, will be trucked over 2 mountain passes across the United States and arrive at the Hayward Test Track late next summer. We see the fruits of all of those hours of design in that hardware. And I want to share with you, in Pittsburgh, their technology team, they fielded question after question from us. They had simulators of our entire BART system there that were up and running, and the employees knew as much about our system as we do. You know, it really built up my confidence in the core product of CBTC that Hitachi STS is delivering for BART and has delivered around the globe. So moving on to the vehicle. I mentioned earlier what it takes for BART forces to convert a train to be CBTC equipped. Let's look at the specifics. We have 2 types of cars in our fleet of the future. D cars that are the cab cars, and E cars that are non-cab cars. What we see here is a showcase of the where and what equipment goes on a D car. On the top, a roof antenna. In the cab is that car-borne controller. This goes in the cab of the cars. On the axles, holes are drilled and a speed sensor and bracket are attached. This provides us with one of the most important parameters, the speed of the car. The vehicle, software, hardware, and wayside equipment, they all come together to deliver a signaling system that becomes its greatest value when used by operations. It touches all our operations employees and requires training operators at Operations Control Center, maintenance teams who service the equipment, train operators who will use an over and back switch to move between CBTC territory and track circuits during the migration. Implementing CBTC is not an easy journey, but it's worth it. And like other technology, once it's in place, you wonder how you ever lived without it. And now I teased earlier on showing you the migration plan. Here it is. So on the left side is the proposed migration plan overlaid on the system map. Migration means converting over that area with CBTC to run CBTC equipped vehicles with CBTC wayside, basically operating with under CBTC. The first phase 0, shown at the Hayward Test Track, is where this track is in the process of being converted over to a CBTC test track, where the whole system will be tested. This is the location where that first train control hut will be installed. Phase 1 is at the OCC. This is where computers, servers, racks, and that automatic train supervision software is installed at the OCC. Now, on the lower left corner, you see phase 2. This is from Millbrae to Colma. With migration complete in this area, it would be the first time riders experience a train running with CBTC. This phase 2 represents the area where our most fragile and sensitive signaling system is. This outdated equipment is difficult to acquire and it has frequent faults. There is an urgency to replace this specific signaling system on the W line. The project has some strategies to accelerate completing phase 2, such as running what's called a captive fleet, which is a fleet that CBTC converted and dedicated to run on the lines that go to SFO, instead of converting over all of the vehicles at once. I mentioned earlier about this phased approach. Everything is phased, including this captive fleet. Another option is resequencing a test track at Dublin to after the W line is nearly complete to keep the construction forces focused on the W line. In the 2-year look-ahead schedule on the right, what pops out is the amount of ongoing parallel work. The Phase 2 W line is at the bottommost portion of the schedule. It is currently under design with construction beginning mid-next year in this area. There are 4 pilot cars that will be the first to be retrofitted and tested on the Hayward test track. By mid-25, production cars will begin being retrofit by the BART forces. We are committed to meeting the current FFGA commitment of 28 trains through the Transbay Tube by 2030. This is a generational project, and thank you to those who had the early vision to see it through thus far. And a special thank you to Dave Hart, our RS&S chief, who is to be up here with me, but retired yesterday.